In 1943, Allied generals began to understand something that terrified them more than the Luftwaffe or German armor. It was not the enemy's firepower that kept their armies from advancing. It was geography. A single destroyed bridge could stop 10,000 men, strand 300 tanks, cut off supplies, delay an entire offensive for days, and turn victory into a stalemate. Every time the Germans retreated, they did not just fall back, they erased the landscape behind them. Rail lines, overpasses, culverts, river crossings. Every artery of movement vanished in fire and steel. The Allies could win any battle, but they could not cross water fast enough to finish the war. That was the nightmare of the European campaign. Every advance ended the same way. A river, a gorge, or a canal turned into a wall. A column of tanks halted in the mud while engineers crawled forward to inspect a mangled structure still burning from German charges. The bridge deck gone, steel trusses twisted like paper, support piers cratered by demolition mines. What had been a road an hour ago was now a 100-foot gap under artillery fire. Infantry waited on one bank, the enemy regrouped on the other. And by the time the Allied engineers could throw together a temporary crossing, the window for pursuit was gone. By the winter of 1942, the problem had turned strategic. In North Africa, Allied forces learned that terrain could be as deadly as any German weapon. When the Africa Corps pulled back from Tunisia, every wadi, every dried riverbed became a barrier. Pontoon bridges collapsed under tank weight. Makeshift timber spans burned or snapped. Engineers joked bitterly that we can build a bridge anywhere as long as no one drives across it. The Royal Engineers, Britain's combat construction corps, had been fighting this losing battle since Dunkirk. They had dozens of bridging systems on paper, none of which could deliver what the Army needed. A portable, modular bridge strong enough to carry heavy armor, yet light enough for men to assemble without cranes or welding equipment. Existing systems were either too weak or too complicated. The Inglis tubular bridge required massive pipes and heavy bolting. The Callender-Hamilton truss needed mechanical hoists. Everything demanded trucks, cranes, or days of preparation. None could be built fast enough under fire. In 1940, a quiet man inside the British War Office started sketching an alternative in the margins of his reports. His name was Donald Bailey, a civil servant with a mild stammer and a fascination with mechanical puzzles. He was not a field engineer or an officer. He had never commanded men in battle or built anything larger than a model railway. Yet he had an instinct for geometry and simplicity. He looked at the problem not as an engineer, but as a builder of systems. What if the bridge was not one solid structure, but a kit made of identical pieces that any soldier could carry and connect, like a child's construction set? Bailey's concept was brutally practical. Instead of massive girders, he designed 10-foot-long rectangular steel panels with cross-braced lattices that could be joined together with simple pins and bolts. Each panel could be handled by 6 men and carried on a single truck. They could be assembled side by side for width or stacked vertically for strength. The sections would rest on rollers, allowing the entire bridge to be built on the near bank and then pushed forward over the gap. No need to send men into the river or under enemy fire. The bridge would effectively build itself across the water, one section at a time. In 1940, he presented the idea to his superiors at the Experimental Bridging Establishment in Christchurch. They were skeptical. The idea seemed too fragile, too simplistic. No general wanted to hear that a few bolts and panels could replace the complex, field-proven trusses of the Corps of Engineers. But Bailey built a prototype anyway, by himself, from scrap steel. On a cold November morning, he and a handful of engineers tested it across a drainage ditch outside the facility. They assembled it in less than an hour. A 3-ton truck drove over it without a sound. Then a tank rolled onto it. The bridge flexed, groaned, and held. The reaction was immediate. What Bailey had built was not just a new bridge, it was a new philosophy. Military engineering had always been about scale, bigger girders, heavier materials, stronger supports. Bailey's design inverted that logic. It relied on distributed strength. Each panel carried part of the load, and the whole structure shared the strain. The more panels you added, the stronger it became. It could grow or shrink like a machine, adapting to any river or road. In 1941, the War Office approved mass production. Bailey bridges were built in secret at British steelworks, their parts shipped in crates labeled only by number. Each crate contained everything needed to build a span: panels, transoms, stringers, bolts, pins, and rollers. The only tools required were spanners and muscle. Assembly instructions fit on a single page. Within weeks, field units were training to erect the new bridge under simulated combat conditions. The first combat test came in North Africa in late 1942. The 8th Army faced a series of destroyed crossings near Medjez El Bab, Tunisia. German engineers had done their job well. Every major road bridge was blown, every alternate route mined. The Royal Engineers unpacked their new weapon, the Bailey Bridge. In less than 6 hours, using trucks, manpower, and floodlights, they spanned a 100-foot wadi, strong enough for 40-ton tanks to cross. At dawn, British armor rolled across. The Germans had assumed the river would delay pursuit for 2 days. Instead, the attack resumed before breakfast. From that moment, commanders realized what they had: a weapon not of destruction, but of momentum. The Bailey Bridge turned water from a barrier into an inconvenience. Engineers could carry it anywhere, assemble it anywhere, and reuse it endlessly. The same panels that crossed a Tunisian wadi one week could be dismantled and rebuilt over an Italian gorge the next. When Allied planners began drawing up operations for Sicily and Italy, they knew that German retreat tactics would again rely on demolition. In the Italian mountains, where every valley ended in a river and every road clung to a cliff, destroyed bridges could paralyze entire corps. But this time, the British and American engineers had an answer. Shiploads of Bailey components were loaded in Alexandria, Oran, and Liverpool. Each bridge set was standardized: 380 panels, 60 transoms, 24 rollers, and bolts, enough to build a 150-foot Class 40 bridge capable of supporting a 40-ton tank. The Italian campaign became the bridge's proving ground. At the Sangro River in 1943, Bailey spans carried supply trucks under constant artillery fire. At the Garigliano, engineers built a 200-foot triple truss strong enough for the massive Churchill tanks to cross. At Cassino, where rivers turned into quagmires, soldiers assembled Baileys while shells exploded within yards. They learned to build by feel, tightening bolts by instinct in darkness and mud. Casualties among engineers were brutal. Some units lost half their men in a single night, but the bridges kept rising. The statistics were staggering. By the end of 1943, over 300 Bailey bridges had been built in Italy alone. The record for the longest single span stood at 240 feet. The fastest full bridge assembly under fire took 3 hours. One U.S. engineer wrote home, "We can cross a river faster than the Germans can blow one up." That sentence became the unofficial motto of the Allied advance. Every soldier who saw one remembered the first time he drove across it. The rhythmic clang of steel plates under the treads, the echo of bolts shifting under load, the smell of oil and river mud. It didn't look like much, just a lattice of panels bolted together, but they all knew it meant one thing: the road forward was open again. For commanders, the strategic impact was revolutionary. Before the Bailey, river crossings required days of preparation, bridging equipment convoys, and coordination with engineers and sappers. With the Bailey, every infantry division carried its own bridge in sections. The bridge was no longer a specialized asset. It was a standard tool. A single battalion could move, assemble, and deploy a crossing within hours. That flexibility changed operational planning. Generals could attack where the enemy least expected, knowing that rivers and gorges no longer dictated the lines of advance. The bridge's modular nature also made it nearly indestructible in logistical terms. Damaged sections could be replaced instantly. Entire spans could be lifted, shortened, or reinforced, depending on need. In a war of attrition, where speed meant survival, that adaptability was priceless. But the most remarkable thing about the Bailey Bridge wasn't its design. It was who built it. Thousands of civilians across Britain, mostly women, worked in factories welding the panels and packing them into crates. They had no idea their work would shape battlefields across 3 continents. Each time an army advanced, their steel carried it forward. By early 1944, Bailey bridges were part of every Allied operation order. American, British, Canadian, Indian, and Polish engineer units all trained on the same system. They called it the bridge that built the war forward. Every major advance, Salerno, Cassino, Anzio, depended on it. The Germans noticed. Their own bridging systems were heavier, slower, and required cranes. Field reports from captured Wehrmacht engineers admitted that they could not understand how the Allies crossed rivers so quickly. One report from the Italian front read, "Enemy possesses portable bridges of great strength, evidently prefabricated, capable of supporting tanks. Impossible to counter with demolition tactics." By the time the Allies were preparing for Normandy, the Bailey Bridge was no longer an experimental weapon. It was standard issue. And when the invasion came, it would prove that the simplest idea of the entire war, a box of steel panels and bolts, could move faster than any army ever had before. The war that had once stopped at every river was about to find a way across them all. By the spring of 1944, the Bailey Bridge was no longer just an invention. It was the backbone of Allied mobility. What had started as a strange British experiment, assembled by hand in muddy fields, had become one of the most heavily produced military engineering systems in history. The armies preparing to invade Western Europe depended on it completely. The success of Operation Overlord, D-Day, did not rest only on the soldiers storming the beaches or the tanks breaking through the hedgerows. It depended on whether the engineers behind them could keep the roads moving, the supplies flowing, and the tanks rolling. Without bridges, no advance lasted more than a day. Donald Bailey's system had grown into an empire of steel. Dozens of factories across Britain were building bridge panels around the clock. Steelworks in Birmingham, Middlesbrough, and Glasgow fabricated the 10-foot panels, welding and riveting in shifts that never stopped. Each panel weighed 570 pounds, light enough for 6 men to carry, but strong enough to hold a 40-ton load when joined in trusses. Thousands of bolts, pins, and clamps poured out of machine shops and assembly lines run by women. Women who never saw a battlefield yet carried the weight of armies in their hands. The genius of Bailey's design lay not in complexity, but in brutal, functional simplicity. The bridge was a kit, standardized, modular, and infinitely adaptable. A single bridge bay consisted of 3 components: transoms, stringers, and panels. Add more bays, and you had more length. Double the panels on each side, and you doubled the strength. Stack the panels vertically in 2 or 3 tiers, and the bridge could carry heavy tanks. Every piece connected by hand, with no cranes or welding. A soldier could join panels by aligning the pinholes and driving the steel pins with a hammer. The entire system was so foolproof that an infantry platoon could build one under shell fire without written instructions. The engineering was extraordinary because it accounted for everything that could go wrong in combat. Bailey's team tested panels under explosions, overloading them until they bent but never broke. They designed a launching roller system so that engineers could assemble the bridge on the near bank and push it forward across the gap, bay by bay, until the far end touched the opposite shore. No one had to enter the river where German snipers or machine guns could slaughter exposed men. If the enemy shelled the construction site, the partially built bridge could simply be rolled back into safety. The logic was mechanical but ruthless. Build fast, survive, advance. At every level of command, officers realized that the Bailey Bridge changed the mathematics of movement. It allowed divisions to move as if terrain no longer mattered. Before, a single river crossing could delay an army for 72 hours. With Bailey bridges, that delay dropped to 12, sometimes less. The average Bailey team could erect a 120-foot Class 40 span in 6 hours under favorable conditions. A veteran crew could do it in 4. The record, set in Italy by Canadian engineers near Ortona, was just 2 hours and 50 minutes from the first pin driven to the first tank crossing. The Normandy landings put this efficiency to the ultimate test. On June 6, 1944, Allied forces landed in France with over 1,200 sets of Bailey Bridge components packed in ships and landing craft. The beaches were not the true obstacle, the rivers and hedgerows beyond them were. German engineers had spent months blowing every culvert, bridge, and overpass in northern France. Within 24 hours of the landings, Bailey bridges were being assembled under fire across flooded ditches and irrigation canals behind the beaches. In the days that followed, they became the arteries of the invasion. One of the most remarkable of these early builds took place near Bayeux, where the 50th Northumbrian Division needed to cross the river Sulas to push inland. German artillery had destroyed every existing bridge. Under continuous shelling, a team of Royal Engineers began assembling a Bailey span at midnight. They worked by the light of burning vehicles, hammering pins into place while shells whistled overhead. When a section collapsed under fire, they replaced it within minutes. By dawn, a 40-ton Churchill tank rolled across to support the infantry on the far side. The entire operation took 5 hours. In that single night, the difference between victory and disaster came down to a few hundred steel panels and the men who carried them. By late June, as the Allies broke through the Bocage country, Bailey bridges became as common as rifles. Every division had its own bridging company, every company had trained teams, and every convoy carried spare panels. The bridges connected tank columns, replaced bombed rail crossings, and spanned the craters left by retreating Germans. They became so vital that Eisenhower himself described them as one of the 3 most important inventions of the war, alongside radar and the landing craft. The figures were staggering. Between D-Day and the fall of Paris, Allied engineers built more than 2,000 Bailey bridges across northern France. Combined, their total length exceeded 40 miles. One single corps of engineers, the British 8th Army's 15th Field Company, built over 20 bridges in 2 weeks during the Normandy campaign, averaging one every 16 hours. Each bridge carried thousands of tons of supplies, fuel, ammunition, rations, and men. The bridge's modularity meant that even destroyed sections could be rebuilt from captured parts. German forces began to use abandoned Bailey panels themselves, reassembling them into makeshift defenses or roadways. Reports from the front mention enemy use of English bridge material in retreat zones. The irony was clear. A British invention was now helping the German army escape faster. In August 1944, during Operation Cobra, the breakout from Normandy, the Bailey Bridge proved its worth beyond calculation. American armored divisions racing toward Avranches needed to cross rivers faster than the Germans could regroup. Engineers moved ahead of the tanks, building bridges in the dark, sometimes within range of enemy mortars. When one crossing collapsed under the weight of a Sherman tank, the engineers rebuilt it overnight. By dawn, the entire column was moving again. The same pattern repeated day after day: advance, demolitions, bridge, advance again. The Bailey was not elegant. It rattled, flexed, and groaned under load. When tanks crossed at speed, the sound was deafening, a metallic thunder that vibrated through the ground. Soldiers said they could feel the panels breathing under the weight. But it worked. No other bridge system in the world could have done what it did, at the speed it did it, with the resources available. By the time the Allies reached the Seine, the Bailey had become part of the daily rhythm of war. One British report recorded that a single engineer company carried enough parts to build 3 separate bridges simultaneously. The system was so efficient that logistics officers began using Bailey components to replace bombed railway bridges, allowing trains to resume supply runs within days. The front advanced faster than any staff planner had predicted. What made it all possible was the bridge's brutal logic. Every piece was designed for hand labor. A 6-man team could lift a panel, carry it across uneven ground, and slot it into place. No single component weighed more than a man could handle. Assembly required no electricity, no cranes, no special tools. Even if half a team was killed or wounded, the survivors could continue the build. The system was idiot-proof because war left no room for elegance. And yet, despite its mechanical simplicity, the Bailey Bridge was a masterpiece of structural engineering. The truss design distributed loads along the upper and lower chords through the diagonal bracing, converting vertical force into tension and compression in perfect balance. Every bolt, pin, and gusset plate had been tested under stress far beyond combat conditions. Field failures were almost non-existent. Reports from Italy and France showed an average lifespan of 6 months under constant use, unheard of for a temporary bridge. Some remained in service for years after the war, carrying civilian traffic. Behind the frontline success lay a logistical machine of staggering scale. By 1944, British factories were producing 25,000 tons of Bailey components every month. The total output for the war would exceed 650,000 tons, enough to build a continuous bridge from London to Berlin. The entire system was standardized to the point that parts built in Canada could be joined seamlessly with those made in Glasgow or Detroit. The Allies had created the first truly global modular construction system years before the term existed. Engineers quickly adapted the design for every conceivable purpose. There were double-double and triple-single configurations for different load classes, pontoon-mounted Baileys for amphibious crossings, and Bailey deck variations for railways. The design even extended to prefabricated roadways laid over mud or rubble to create instant causeways. Each adaptation followed the same principle: speed, strength, and interchangeability. The Germans could not match it. Their own field bridges, like the Kastensteg and Krupp-type trusses, required heavy cranes and took days to erect. Captured reports described Allied bridging as immediate, mechanical, and unstoppable. The Wehrmacht had relied on destruction to buy time. The Bailey erased that advantage. Every demolished span now represented only a few hours' delay instead of a week. The psychological effect was immense. Soldiers who once cursed every river crossing began to see them as challenges, not disasters. When reconnaissance reported a destroyed bridge ahead, the response was no longer panic. It was routine. "We'll Bailey it," became the standard answer. That phrase carried a quiet confidence that hadn't existed before. The troops trusted the bridge because it had never failed them. As the Allies advanced deeper into France, the Bailey became a symbol of relentless progress. Civilians watched in disbelief as British and American engineers erected entire bridges overnight, while artillery still thundered in the distance. French villagers nicknamed them Ponts Miracles, miracle bridges. For soldiers who had slogged through Italy's mud and North Africa's sand, the sight of those lattice steel trusses stretching over a river meant one thing only: the road home. By September 1944, when the Allies reached Belgium, over 3,000 Bailey bridges had been built since D-Day. The longest of them, spanning the Orne near Caen, measured more than 350 feet. Another, built by Canadian engineers across the Seine at Vernon, carried 40,000 vehicles in its first week. Not one failed under combat load. The Bailey Bridge had turned the concept of engineering support into a weapon of speed. It was no longer just a bridge. It was a statement. Nothing the enemy could destroy would stay destroyed for long. Each time a span went up, it told the Germans the same thing, that their retreat could not save them, their demolitions could not delay the inevitable, and their rivers could no longer protect them. By the time the Allies reached the Rhine, Donald Bailey's creation had already done the impossible thousands of times. The bridge that could be carried by 6 men had carried the entire weight of the war. And the final test, the crossing of the Rhine itself, was about to prove just how far that simple invention could push the limits of physics, logistics, and human endurance. By March of 1945, the war in Europe had reached its final barrier, the Rhine. Every German city west of it had fallen, every stronghold broken. Yet this single river, wide, fast, and heavily defended, stood as the last obstacle between the Allies and the heart of Germany. The Rhine was no ordinary river. It was a natural fortress, hundreds of meters across in places, lined with steep banks and fortified with anti-aircraft guns, artillery, and machine gun nests. German High Command had ordered that no enemy should ever cross it intact. Bridges were wired with explosives, charges placed on every span, demolition crews waiting for the signal. When retreating units reached the east bank, they blew the bridges behind them, leaving only fire and wreckage. The Allied armies reached the river's western edge in early March and found the landscape littered with twisted girders and smoking craters. The Germans had carried out their scorched earth orders with precision. In 1 week, they destroyed over 40 major bridges along the Rhine's length. It was the same tactic they had used in Italy, France, and Belgium, but this time the Allies were ready for it. The Bailey Bridge had changed everything. For weeks before the crossing, engineers from British, Canadian, and American units had been rehearsing for the biggest bridging operation of the war. They studied aerial photographs of the Rhine's bends and currents, calculated water flow speeds, and built mock-up crossings in England and France. Every possible obstacle was planned for: currents, underwater debris, artillery fire, and Luftwaffe attacks. The operation required coordination between thousands of men: infantry to secure the banks, engineers to assemble the bridges, artillery to suppress enemy positions, and supply convoys to keep the work going through the night. The stakes were absolute. The Allied plan, codenamed Plunder, called for simultaneous crossings at multiple points. The British Second Army would cross near Rees and Wesel, supported by Canadian units, while the U.S. Ninth Army crossed further south at Rheinberg. The U.S. First Army under General Hodges would move toward Remagen, where intelligence reports mentioned a damaged but still standing bridge, the Ludendorff Bridge. It would become the first and most famous crossing of the Rhine, and Bailey bridges would soon follow it. On March 7, 1945, an American reconnaissance patrol reached Remagen and saw something unbelievable. Through the smoke and haze, the Ludendorff Bridge still stood, its steel arches scarred by explosions but intact. The German demolition team had detonated their charges too early, damaging but not collapsing it. For the first time in the campaign, luck favored the Allies. The Americans rushed forward under fire and captured the bridge before the Germans could finish the job. Tanks and infantry began streaming across immediately, even as engineers worked underneath to reinforce the damaged structure with Bailey panels and steel beams. That moment, soldiers crawling across a half-ruined bridge while shells exploded around them, became one of the most iconic images of the war. The Rhine, which had symbolized Germany's invincibility for centuries, had been breached. But the Ludendorff Bridge could not last. Its structure was too badly damaged, and within days, constant artillery fire and overuse caused it to sag dangerously. Engineers knew it was only a matter of time before it collapsed. They needed replacements, fast, strong, and reliable. That was when the Bailey Bridge once again became the instrument of momentum. Within 24 hours of the Remagen crossing, U.S. Army engineers began assembling 2 Bailey pontoon bridges alongside the damaged Ludendorff span. Working in freezing rain under direct artillery fire, they launched sections from the western bank using steel pontoons anchored in the current. Each bridge bay was rolled out on temporary tracks and pushed forward into the water, where it floated on pontoons until it locked into place. The noise was deafening, hammering pins, shouting men, engines roaring as trucks brought new panels to the water's edge. Artillery shells fell around them, sending geysers of mud and river water into the air. But the work never stopped. By the third day, the first of the Bailey Bridges was complete, a 1,032-foot floating structure capable of carrying 40-ton tanks. Within hours, Sherman tanks and half-tracks were rolling across, their weight pressing the pontoons deep into the river's surface as the steel trusses groaned under strain. A second, heavier Class 70 bridge followed, reinforced with triple trusses to handle the largest vehicles in the Allied arsenal. The German defenders on the far bank could only watch as the unstoppable machine of Allied logistics rolled over a river they had sworn could not be crossed. The statistics of the Rhine crossings were staggering. Over 6,000 engineers, supported by 20,000 infantry and 3,000 vehicles, worked around the clock to build and maintain bridges across the Rhine's 820-foot width. Between March 7 and March 31st, Allied forces constructed more than 30 major bridges, many of them Bailey spans, along the river. Each one became a lifeline for entire divisions. In just 2 weeks, more than 1 million men, 200,000 vehicles, and 500,000 tons of supplies crossed into Germany. The speed of the advance stunned even Eisenhower's staff. At the British crossing near Rhine, the Royal Engineers built one of the longest Bailey bridges of the entire war. The Blackfriars Bridge, as it was nicknamed, stretched 1,100 feet from bank to bank, supported by pontoons and resting on steel piers. The operation was a masterpiece of precision under chaos. Artillery barrages shook the riverbanks as sappers assembled the panels by lantern light. Cranes swung heavy transoms into place while teams of men hammered bolts with frozen hands. German shells landed within yards, but the engineers kept working. The bridge was completed in just under 3 days, an engineering miracle by any standard. Photographs taken after the battle show endless lines of trucks, tanks, and armored vehicles moving across Bailey bridges that seemed to stretch forever into the smoke. To the men who drove over them, the structures looked fragile, almost improvised. They flexed visibly under load, their trusses creaking and vibrating with every passing tank. But they held. The same modular logic that had carried the Allies through Africa, Italy, and France now carried them into Germany itself. The German reaction bordered on disbelief. Intelligence reports captured after the war show that Wehrmacht officers could not understand how the Allies were able to cross so quickly. One report from the 15th Army stated, "Enemy engineers have bridging material of extraordinary simplicity and strength. They can cross any obstacle in 24 hours. Our demolitions are ineffective." That sentence, simple and resigned, summarized the end of Germany's defensive strategy. Every tactic that had delayed the Allies for years, destroying bridges, flooding valleys, mining roads, was now useless. The Bailey Bridge had rendered geography obsolete. Beyond the technical triumph, the psychological impact was immense. Soldiers who had spent years slogging through mud and wreckage felt an almost superstitious awe toward the Bailey Bridge. It had become a symbol of inevitability, of progress that could not be stopped. Veterans of the Italian campaign who now fought in Germany said it felt like carrying a piece of home into battle. Wherever a river blocked their path, the same familiar lattice of steel appeared within hours, connecting one shore to another like a promise. "We knew," one Royal Engineer later recalled, "that no matter what the Germans blew up, we'd cross by morning." The logistics behind the Rhine crossings were a marvel of coordination. Bridge components were pre-packed in trucks according to assembly sequence: panels, transoms, stringers, decking, bolts. Each vehicle carried the parts for a specific section of the bridge, so there was no confusion under fire. Supply chains brought replacement parts from depots hundreds of miles away. The entire process worked like clockwork, even under shelling and air raids. The Allies had transformed bridging from an engineering problem into an industrial process. In the days following the crossings, as the German front collapsed, the Bailey bridges continued to multiply. Engineers built over 500 smaller spans across tributaries and canals, ensuring that every supply route remained intact. Roads were rebuilt on steel decking, railways reconnected using Bailey frames, and armored columns advanced faster than their fuel convoys could keep up. The Rhine, once considered an impregnable line, had become just another milestone. General Montgomery, overseeing the northern crossings, later said that without the Bailey Bridge, we would still be sitting on the West Bank. Eisenhower's staff agreed. In post-war reports, the Bailey was credited as one of the 4 critical factors that enabled the Allies to end the war in Europe in less than a year after D-Day. The other 3 were air supremacy, logistics, and intelligence. The bridge stood equal among them. By late April, Allied forces had crossed every major river barrier in Germany. The bridges built at Wesel, Remagen, and Oppenheim carried entire armies toward the Elbe. Some of them remained in use for months after the war, supporting occupation forces and relief convoys. Others were dismantled and shipped to rebuild civilian infrastructure. Wherever they stood, they symbolized the same idea, that no obstacle, geographical, mechanical, or man-made, could withstand organization, ingenuity, and sheer will. The Rhine had been Germany's last hope of containment. For centuries it had marked the boundary of empires. The Romans, the Franks, Napoleon, all had seen it as a line of defense. But in 1945, a bridge designed by a British draftsman and assembled by soldiers under fire erased that line forever. The war was now an open road. When the Ludendorff Bridge finally collapsed on March 17th, killing dozens of engineers working on it, the riverbank was lined with Bailey spans that carried on without pause. The sound of collapsing steel was drowned out by the continuous rumble of engines moving east. The enemy had destroyed his own defenses faster than the Allies could use them. In the words of one U.S. Army report, our engineers defeated the geography of Europe. It was not a boast, it was a fact. The Rhine crossing marked the moment when the Allied war machine became unstoppable, and at the heart of that machine stood a structure that could be carried by 6 men and assembled with nothing more than hammers and muscle. In the months after the victory, military historians would look back on the Rhine crossings as a turning point, not because of strategy or luck, but because of logistics. Every tank that rolled into the Ruhr, every truck that carried food and ammunition to advancing divisions, did so over steel trusses bearing the same stamp, Bailey Bridge, Class 40. That small inscription, welded into every panel, had become a quiet signature of triumph. It stood for something more than a piece of engineering. It represented the ability of organized human effort to outthink destruction. When the Allies crossed the Rhine, they did not just conquer Germany's final river. They crossed the boundary between war fought with brute force and war won by design. And when the armies rolled off the far bank, leaving the shattered ruins of the German defenses behind them, they carried with them the proof that no fortress, no obstacle, no line on a map could withstand the will to build faster than the enemy could destroy. When the guns finally fell silent in May 1945, the world that remained was a skeleton of what it had been 6 years earlier. Europe was a continent of wrecked cities and burned railways, its roads cratered, its rivers choked with the twisted remains of bridges destroyed by both sides. Yet across this landscape of ruin stood a pattern of steel latticework, thousands of Bailey bridges spanning rivers, valleys, and bombed crossings. They had been built as temporary structures, but by the time the peace was signed, they had become the arteries of survival. In the immediate aftermath of the war, the Allied armies faced a new kind of crisis. The same logistical genius that had carried them into Germany now had to feed millions of civilians. Roads were impassable, railways had been obliterated, and entire towns were cut off by destroyed bridges. The Bailey Bridge, built to move tanks and guns, became the tool that moved bread and medicine. The same engineers who had once assembled bridges under artillery fire now worked under the direction of military governments and relief agencies, rebuilding routes so that convoys of food and fuel could reach starving populations. Between May 1945 and January 1946, the Royal Engineers alone built or repaired more than 2,000 Bailey bridges across Germany, Austria, and the Netherlands. American and Canadian units added hundreds more. Most of these bridges were never intended to last beyond a few months, yet some would stand for decades. In Hamburg, the Allied Control Commission ordered a triple-truss Bailey to replace a destroyed railway bridge over the Elbe. It carried civilian trains until 1955. In the Netherlands, a Bailey span near Nijmegen that had once carried Sherman tanks now carried farmers and cyclists to market. The bridge that had been invented to win battles became the first instrument of reconstruction. And that transformation, military innovation turned into peacetime infrastructure, was the final proof of its genius. Donald Bailey himself, by then back in London, was a reluctant hero. He had received a knighthood from King George VI in 1946, an honor that embarrassed him more than it pleased him. When reporters asked how it felt to have created the bridge that won the war, he replied, "It wasn't me who built it. It was the men who carried it on their backs." He meant it literally. Soldiers had lifted those 570-pound panels through mud, under gunfire, in snow and desert heat. Bailey saw himself as a draftsman who had provided them with a tool, nothing more. Yet among engineers, his name was now spoken with the same respect given to the designers of the Spitfire or the Liberty ship. In the factories that had produced the bridge components, production lines that once rang with the sound of rivets and hammers now turned to peacetime work. Companies like Cleveland Bridge and Engineering and Braithwaite Manufacturing converted their Bailey assembly jigs to build water towers, railway platforms, and oil refineries. Many of the welders and machinists who had built Bailey panels were women, and they carried that skill into civilian industry, transforming British engineering culture. For the first time, the techniques of wartime mass production, modularity, standardization, field assembly, were applied to civilian construction on a global scale. The Bailey Bridge's post-war journey was not limited to Europe. The British government, recognizing its usefulness, began exporting surplus bridging kits to countries struggling to rebuild. India, Burma, and Malaya received hundreds of sets through the Colonial Office. In 1948, Bailey bridges carried supplies across flood-damaged rivers in Assam. In 1950, they became vital during the monsoon emergencies in Ceylon. Wherever infrastructure collapsed, those lattice trusses appeared again, carried on trucks, assembled in hours, and left standing for years. In 1950, the Korean War began, and once again, the Bailey returned to combat. American and Commonwealth engineers used it across the Korean peninsula's mountainous terrain, building over rivers that flash flooded without warning. At the Han River crossing near Seoul, engineers built a 1,200-foot Bailey in freezing rain, using arc lamps for light and bulldozers to anchor the pontoons against the current. It carried convoys for 3 years. The bridge had become more than an artifact of World War II. It was now part of military doctrine itself, a permanent element of modern warfare. What made the Bailey different from any other wartime invention was its endurance. Aircraft and tanks became obsolete within a few years. Even ships and guns were replaced by new models. But the Bailey Bridge, designed in 1940 by a man with a pencil and a ruler, remained unchanged for decades. The same panels, pins, and transoms built in wartime factories were still being used in the 1960s, the 1970s, and in some countries, even into the 21st century. Its geometry had no need of improvement. Engineers could build longer spans and higher load classes simply by doubling or tripling the trusses. Its simplicity was its immortality. In 1952, a study by the U.S. Army Corps of Engineers compared all available military bridging systems, American, German, Soviet, and British. The Bailey ranked first in strength, speed, and adaptability. The report concluded, "No other bridge can be erected by hand labor to carry such loads over such distances in so little time." That single sentence was the distilled essence of its value. The bridge's post-war civilian life was equally remarkable. In the years following the war, as Britain faced economic austerity and material shortages, Bailey bridges provided emergency replacements for collapsed railway lines, flood-damaged roads, and even urban overpasses. In 1947, when the River Severn flooded and destroyed key crossings, Royal Engineers used wartime Bailey panels to reopen the routes within days. The same thing happened after floods in Scotland and Wales. The bridges that had once carried tanks now carried coal trucks, ambulances, and mail vans. In 1953, when the North Sea storm surge destroyed dikes and bridges across eastern England and the Netherlands, Bailey spans were rushed to the scene by rail. Photographs from that disaster show soldiers in uniform alongside civilians, bolting together the same steel panels that had crossed the Rhine 8 years earlier. One Dutch newspaper called it the bridge that always returns. Beyond Europe, newly independent nations adopted the Bailey as a foundation of their infrastructure programs. In India, engineers used surplus British stockpiles to connect remote mountain communities. In Africa, Bailey kits were shipped to Kenya, Uganda, and Nigeria, forming the first modern highway links in regions where no permanent bridges had ever existed. The bridge became a symbol of functional modernity, cheap, modular, and strong enough to survive floods and decades of heavy use. Donald Bailey, who continued to work for the British government until his retirement in 1962, received countless letters from soldiers and engineers around the world thanking him for his design. One came from a Canadian officer who had crossed over Bailey bridges from Sicily to the Rhine and later used the same system to rebuild roads in post-war British Columbia. He wrote, "Every time I see one of your bridges, I know we still have a way forward." Bailey kept that letter framed above his desk until his death in 1985. Historians who studied the war in later decades began to recognize the Bailey Bridge not just as a piece of hardware, but as a case study in how design could change strategy. It had done more than connect two sides of a river. It had changed the speed at which armies could move, altering the rhythm of modern warfare. Before the Bailey, logistics dictated battle. After it, logistics obeyed the engineer's timetable. The bridge was a practical embodiment of a new military idea, that mobility was power, and the nation that could rebuild faster than the enemy could destroy would always win. During the 1960s, NATO standardized the Bailey Bridge across its armies, ensuring compatibility among allied nations. Updated versions were built from high-tensile steel and aluminum alloys, but the structure itself remained unchanged. The modular principle pioneered by Bailey became the foundation for countless engineering systems, prefabricated housing, modular airfields, and emergency pipelines all drew from its logic. Even in the early Cold War, when nuclear weapons redefined strategy, the Bailey Bridge quietly remained in every military engineering manual. In the 1970s, when American forces withdrew from Vietnam, they left behind hundreds of Bailey bridges that had carried supply convoys across jungle rivers and canals. Decades later, those same bridges, rusted but still standing, continued to serve rural communities. Local farmers built homes under them, children played on their decks, and buses still rumbled across them. The lifespan of a temporary Bailey was measured not in months, but in generations. In the early 1980s, a British engineering journal published an article titled "The Bridge That Wouldn't Die." It noted that there were still more than 4,000 Bailey bridges in use worldwide, many of them original wartime structures. Some had been coated in concrete, others reinforced with new steel, but the latticework of Bailey's design was unmistakable. The article ended with a sentence that captured its legacy perfectly. "No bridge has ever carried more men across more rivers under greater pressure." Even today, more than 80 years after its invention, Bailey bridges continue to appear wherever disaster strikes. When earthquakes hit Nepal and Pakistan, when floods cut roads in Bangladesh or Peru, when hurricanes destroy bridges in the Caribbean, engineers reach for the same solution: steel panels, 10 feet long, bolted by hand, strong enough to carry rescue trucks. In those moments, the ghosts of the Royal Engineers from 1943 are still at work, their bridge spanning not just rivers, but time itself. The Bailey Bridge did not end with the war. It outlived it. It became the quiet monument to a truth that every soldier and every engineer learned the hard way. Victory is not only about destruction, but about the ability to rebuild, to cross what was meant to divide, to keep moving when everything else stops. Its steel panels may rust, its bolts may loosen, but the idea behind it, the belief that men with the right tools can overcome anything, remains unbreakable. When Donald Bailey died in 1985, his obituary in the Times was brief. It called him a civil servant whose invention allowed the Allied armies to advance. But those who had crossed his bridges knew better. They knew that his invention had done more than advance armies. It had kept civilization moving when the world had fallen apart. And in the decades since, every time a new Bailey Bridge is built in a flood zone, a war zone, or a disaster area, it carries the same invisible inscription written across its panels in the language of engineers and soldiers alike. Built in haste, stands forever.